So each of these things, connection successful. Okay, got it. Each of these things then is controlling for the other. So there's only one situation in which what you would get for your slopes would be different if you had both predictors in the model or just one or the other. Any guesses as to when it wouldn't matter if x1 and x2 were both in the model, or say just x1? When would the predictor slope differ? Any guesses? I'd love to. So if you have, say, x1 is a predictor in the model, and you add x2, under what circumstance would the slope for the original x1 predictor not change? Any guesses? Yeah, when there's no overlap, exactly. If x1, if there was, yep, exactly right. No overlap. Overlap means covariance in statistics terms, right? Or correlation. I'll take either one of those. So if x1 and x2 are not related to each other at all, then their unique effect will be the same thing as their effect would have been in the first place. That happens rarely in practice. It can happen in experimental designs where you can perfectly associate or not associate things. So let's say that you had a study in which you had 10-year-olds and 11-year-olds, and you had them do one of two different tasks, right? You could assign them so that every combination of age and task had the same number of people in it. Then if you put in a dummy code for whether they were 10 or 11 and a dummy code for which task they did, those predictors would be unrelated because of the way you set up the design. So really, only in those circumstances would the predictors not be related. In the real world, they're almost always related, which means that their effects are going to be different when they're in the model all by themselves versus when they're with other predictors. So in terms of strategy, all of the bivariate associations that you know how to do are still helpful. Because if I find out that, say, x1 is related to y, if I don't have anything else in the model, that's a useful piece of information. If I add x2 to the model and the effect of y1 becomes non-significant, meaning that its unique effect is not significant, then I have to know that it's because of x2. Because it was related, it's not related anymore. If I just started with a model that had both predictors in them at the same time, and the effect of x1 was not significant, I wouldn't know if it's because of x2 or just because it was never going to be related in the first place. So trying to sort out what things are related to each other and then what things are still related to each other, those are two different questions. And so the still related is the new part that we're working on now, but it presupposes that you know whether or not something was related to an outcome in the first place, which is what we would examine by putting in predictors one at a time or in bivariate measures of association. So these slopes convey the unstandardized effect of how a predictor creates an expected outcome. So I can't look at the number that goes on beta 1 and say, oh, beta 1 is 4 and beta 2 is 5. That must mean that x2 is more important because its slope is bigger. I can't make those sorts of judgments without considering what the units are because the slopes are unit specific. If what I want to be able to do, though, is to talk about the relative importance of a predictor, like socioeconomic status matters far more than nicotine or something like that, or vice versa, I have to put them onto the same scale. So to be able to compare the relative effects of predictors, we would need to have a standardized solution. One thing to keep in mind in terms of significance is that the standard error for the predictors for each one is going to be in addition to a function of the leftover variance of y and the sample size, which is what we had before, it also now is going to be a function of the unique variance. So the same predictor can have a different standard error in a model where there are other predictors that are highly related to it. The standard error gets higher whenever it's harder to ascertain what is unique about a given predictor rather than common. So in terms of effect sizes, we can do standardized slopes like before. Those allow us to make relative comparisons. So if I have a standardized slope, what that means is that it would be the slope of the predictor if the predictor, all predictors in the outcome were z-scored, had mean 0, variance 1. So they're all put onto the same metric. Then I can say, oh, well, the standardized slope for x1 is 0.2, but the standardized slope for x2 is 0.4. So therefore, x2 is more important, relatively speaking. You have to have the predictors be on the same scale to be able to make those sorts of comparisons. So standardized slopes are often reported in these sorts of models so that people can make those kinds of judgments about what is relatively more important or less important. The other thing that is reported is this squared semi-partial correlation. That is how much of the R square is uniquely captured by the predictor. So the predictor's contribution to the R square is the squared semi-partial correlation. There's a version that adjusts for sample size relative to that. That's called omega squared. I've included in here what programs provide. So in SAS, we can get a squared semi-partial correlation in PROC-REG. We can also get it in Stata as a separate step known as P-core. And so I'll show you how to get those things as well. Let's see, where are we going here? Yeah. The only catch is that the squared semi-partial correlations cannot be used whenever you have more than one slope for a given predictor. In that case, you have to be able to lump the slopes back together again. So I'll show you how to do that. That requires a new statement. The one new piece of programming that you haven't seen yet, it's going to be a statement called contrast in SAS, or it's going to be a statement called test in Stata. So for instance, if I have a model that looks like this, I'm on slide 18, a linear effective age paired with a quadratic effective age. I would need to lump those two slopes back together again to talk about the contribution of age to the model. And so there's a special statement that allows you to lump, so to speak. That's contrast in SAS and test in Stata. Same thing if I had a grouping variable where I had more than one slope to describe the group differences. I have to be able to lump them together to talk about the effective group. And so I'll show you how to do that. All right. Yeah. How are we doing? Good. Questions? I'm eagerly looking at the chat window. Anyone going to type to me or talk to me? No? I'm not frozen, right? Okay, good. All right. So vocabulary. What you can tell people that you now know, by the way. We are talking about multiple regression at this point, when there are multiple predictors, as opposed to simple regression when there's only one. If you have a model that has, say, a grouping variable in it at the same time that it has a quantitative variable in it, that is known as analysis of covariance, ANCOVA, so to speak. So what you guys know of as sort of one general framework, the general linear model, each specific combination within it goes by a different name. And it gets taught that way in other classes. So for instance, the first thing that we did is fit a single quantitative predictor, right? That is simple linear regression. Yep, simple linear regression. If I have a single binary predictor, that is an independent samples t-test. Yeah. If you have, here, I'm muting you, Cheryl, so your dog can bark in peace. And that way Jean Paul's dog doesn't lose his mind. Um, or anyone else's dogs, they're losing their mind. Um, if you have a grouping variable with 3 or more categories as a predictor, that is ANOVA, that is analysis of variance. If I have that grouping variable with a quantitative variable, that is ANCOVA, analysis of covariance. So those names don't necessarily help describe anymore, and they also sort of lump people into false dichotomies as to what you can and can't do at the same time. So that's why I tend to see that they're not as useful. So we're doing multiple regression. Sometimes people throw the word linear in there, and that differentiates it from regressions that predict other kinds of outcomes that are not quantitative. Because you can predict any kind of outcome, you just need a different type of model to do that. So in this situation in which you want to have a grouping variable in the model at the same time as a quantitative predictor. So let's say that I have my golf study, right? Section 1 of homework 4, we had 4 golfing groups. It took 3 slopes to differentiate my 4 groups. What if I had asked you to add the effect of enthusiasm to that model? So to what extent does golf training matter after controlling for enthusiasm, right? That could be a question. In that case, I would want to be able to address the effects of each of the predictors in talking about what contributes to a good golf score. How much does training matter? How much does enthusiasm matter? How much do they each still matter after controlling for the other? The still matter is the unique effect. If I want to talk about enthusiasm, and I only have a linear effect of enthusiasm, that's easy. I have one slope that tells me directly what its unique effect is. If I want to talk about training, that's trickier because training group took 3 slopes to be able to differentiate the 4 means. So I need to somehow lump them back together again. And it turns out our friend F can be used to do that as well. So the F-test of the model is one specific instance of something that's more general, which is known as a multivariate wald test. It's whenever you want to lump slopes together to be able to make a statement about them. So when you're testing the model, you lump all the slopes together that are in the model to talk about the model. And we got, looks like some more connection issues. There's one more joining us. But you can lump anything you feel like and get a test of its joint contribution as well as its unique contribution in the case of having models with more than one predictor in them, and its contribution to the R-square. So I will show you how to do that as well. So whenever you want to know if you've added things to the model and it helps, this technique is useful. Multivariate wald test can allow you to test the addition of more than one thing at a time. We haven't had to do this up to this point because the model had only one variable in it, even if it had multiple slopes, and the model F test that lumps these things together is given for you by default. But when you want to lump slopes together or need to, and it's not a default situation, I want you to know how to do that. So we will show you how to do that in SAS and Stata as well. Let's see. Let me pull up, I think, example 5 before we jump into too much stuff, because then we can do a little bit of review and we can see these things sort of play out. How's that sound? Okay, even though I'm talking to a couple empty chairs. That's all right. So we're done with the general social survey data set. That's done. I am pulling an example data set from my book. So I gave you a reading for this unit from my book. Yay is general. So is that a yay for my book or a yay for dumping the general social survey? Agnostic. Not sure. Oh. Yeah. Did you guys know I wrote a book? I did. It's called Longitudinal Analysis. It took 5 years. Um, no, I don't get any like I don't get any perks of I don't get it for cheaper or anything like that. I can tell you that I am under contract to write a second edition, and that and its original due date was supposed to have been done in March, and that I haven't started yet. So the first edition will be the only edition for the foreseeable future. Yeah, it was over 1,000 manuscript pages. It's 560 pages of print, and I wrote every single word. So so cool. I have grace for the submission. Yes, book editors are so grateful to authors for writing that they basically have to put up with us like never submitting anything. They can't do anything about it. Because we get an advance, so to speak, which is not very much money, but then we don't get anything until the book's done. So they don't get anything, I don't get anything. No one makes money off of these sorts of books. Let me also clarify that. This was a labor of love. I get like $3 or something for every book I sell. It's not a way to make money. Melissa, question? Oh no. Wow, that has not happened yet. I think I would cry. Yeah, it was one of those deals where I've taught a class on longitudinal models for several years and I didn't like any of the textbooks that were out there. So I had like this hodgepodge of chapters from different books that I would try to pull together and they all use different words and different notation and it just and so rather than complaining about it, I decided to write a book and so I did. So you guys get to read chapter 2 of this book because a lot of people try to jump into longitudinal modeling without having a very solid foundation of just regression and linear modeling. And so I wrote a chapter just on that. So I am hopeful to be able to teach longitudinal again sometime. I taught it last spring and it may come back within the next year or two. And you guys would all be invited to take that class if you'd like. But anywho, I wrote a book, and the example for example 5 is from chapter 2 of the book. The entire book is filled with fake data. That way I can hand it out without fear of making anyone angry. So these are simulated data based on a real story. Um, when I was a postdoc at Penn State, I was involved in data analyses for a project called the Octogenarian Twin Study of Aging. That is a mouthful. Octogenarian Twin Study. So they were same sex twins studying genetic components of aging, and they were between the ages of 80 and 100 at the first occasion. So these are older adults, seriously older adults. So I simulated data to suggest postdoc in Happy Valley, yes. And now my internet connection is unstable. Okay, am I back? Okay, we're back again. Okay. Um, so yes, I enjoyed my time in Penn State immensely. It was great. Postdocs are fun. Anywho, so we're predicting an outcome known as information test. It's a measure of crystallized intelligence, so it's like your knowledge of facts and things like that, that in theory should not be affected by aging until you get to some sort of potential disease process that would be interfering. So these data are sort of like the first wave of a longitudinal study. That was it. So there's 550 fake people. Um, I'm going to be predicting their cognition outcome from predictors of age and grip strength. Age is going to be centered at 85 because that was near the mean of the age in the original sample. And grip strength, as odd as it sounds, why that would predict cognition, it's a proxy for physical function that's used in aging studies. I have no idea if that's a useful proxy, but it is. That's a common one. So, in general, you would not predict that someone's grip strength has anything to do with their cognitive status, but in cases of dementia or other sorts of advanced diseases, physical decline is often paired with cognitive decline. So that's why they're interested in measuring both. And there are three groups in the story. Um, with respect to their eventual dementia diagnosis. So the study went on for 8 years, and there were some people who actually already had a diagnosis of dementia when the study started, but they participated anyway to some extent. There were people who got diagnosed during the study, so during the 8 year span, and fortunately, most of the people in the study never were diagnosed. So they didn't have dementia as far as they know up to that during the length of the study. So that is the basis of the three groups here. I have this is SAS code that I'm using to create the contrasts to put group in the model. So it's none, future, or current are the groups. And I'm using none as my reference group. So if the original variable is 1, then I'm going to make two new variables right here. Dem NF stands for none versus future, and Dem NC stands for none versus current. So none is my reference group. They're going to be coded 0. If it's group 2, that's the future group. The first contrast flips to 1 to differentiate the future group from the none group. And if they're in group 3, then the last contrast flips to 1 to differentiate the current group from the none group. So that means the model is directly going to give me the difference of none versus future as one slope, none versus current as another slope, and then I can write a statement to get the difference of those two slopes to get the difference of future versus current, the non-reference group for the model. So I'm centering my predictors here. I'm making two new contrasts for my three groups here, and then I'm adding labels. So this much you guys have already learned how to do, and you get to practice it again for homework 5. Yay! You'll be old hand at it. This extra stuff that's in here, this is just me making things for demonstration purposes. So I am creating copies of these variables that I'm then going to z-score just to show you how to mimic a standardized solution. You don't have to do that. Likewise, you won't have to worry about missing data in your assignments, but in your life you will. And what's going to happen in your models is that anybody who is missing any of the variables in the model is going to get dropped from the data set. Anybody who is missing any of the variables is going to be dropped from the model. So to try and keep the sample size that's used for the analysis constant across models, like no matter which predictor combination is in, I want to have the same group of people. I am preemptively removing cases from the data set that are missing key pieces of information. So in SAS, the way that I'm doing this is using a function. So NMIS is a built-in SAS function that counts the number of missing values. So if the number of missing values across this set of variables that are in my model is greater than 0, then dump them, then delete. That means all of the people who are left have all of the information to stay in all of the analyses that I would want to do. Is it good to dump cases that have missing data? No. Is it necessary? Yes. If you want to take advanced quantitative methods classes, you'll learn about ways of better addressing missing data. It turns out that you can use cases that have incomplete data to some extent if you're willing to make some assumptions about why the data are missing. So that's all I'll say. Oh, Yes. Like, how did I pick the values? Mhm. I did it and then decided which values to use and put them up there. So yes, the proc means is, yeah, right here. So for instance, those were the original variables of age and grip. I looked at the means and said, okay, that looks like 85 would be a good choice, and 9. So yep. The logic is a little bit backwards. Um, it doesn't really matter which constant you pick so long as it's somewhere in the middle, to have a decently interpretable intercept. So age 85 is the predictor that's going to be in my model, which is age minus 85. And grip 9 is grip strength centered. It's 9 pounds per square inch. That's what the units are in this case. Um, Stata folks, I didn't forget about you. So centering age and grip strength is a gen statement. So gen, then the name of the variable you want to create, so the new column that's being created, equals the old variable that's already there, age or grip, and then minus the centering constant. The groups in this case, this looks a little bit different than what you've seen before. There's some extra lines here, but the reason that I did this is to try and get you used to thinking about what happens in real data. So in the Stata code that I had given you before for convenience, I set the first values to be 0 and then systematically changed them to 1 or other things. Do you remember that? Be like gen something equals 0, and then if this, then change the zeros. Well, that's actually not a great strategy, even though it's quicker. Because if somebody has missing data, their score is going to be set to 0 still, even though it should be missing. So what I did here is a more responsible version of that, and it is also what happens in SAS the way that I've coded it. I generated the new columns, but I set them to missing. So equals dot is missing data in both SAS and Stata. Then I went through and reset the missing values to be zeros or ones, conditional on group membership. So if a case did not have a group, so if I didn't know which group they're in, their variables that would go in the model would stay missing. That's the rationale for doing it this way. So replace the new variable equals 0 if they're in group 1, the new variable equals 0 if they're in group 1, replace it to 1 if they're in group 2, and replace it to 1 here if they're in group 3. And then labels. The same idea of the NMIS function in Stata is NMIS here. The Stata function is called rowmiss. That does the exact same thing. So what I'm doing in this step right here is creating a new variable that I'm calling NMIS from the result of this function. So the variable will then take on values as to how many missing values there are in this group of variables. And so then I say, if any of them are missing, drop. So you guys don't have to worry about this for your homework, but you will have to worry about it in life, which is why I'm showing it to you. And then Stata has built-in functions to do z-scoring right here. The S2D function, not to be confused with venereal disease, but z-scores instead. So, see, I can see if you're listening because you're laughing, right? That was funny. Yes, I'm talking about venereal disease in a stats class. All right. So that means if you wanted to, you can get started on your very last homework because all of the first steps are things you already know how to do. Make variables like this, empty model, put one predictor in, and then add another. So the only difference so far is that instead of taking out the predictors that you had before and putting in new ones, in homework 5 you will add cumulatively. So you'll start with one predictor, you'll add a second, and then add a third, and so on. So there's 4 sections in total. But the process of adding each one isn't any different than what you already know how to do. All right. How are we doing? Thumbs up. Are you excited to finish your very last homework and say that you've conquered statistics? Yeah, it's empowering. One way or another, the semester will end soon. We will all get there. So, on that happy note, any other questions before we call it a day? Nope. Okay, then how about we call it a day? Office hours at 3:15 if anybody wants to chat with me. And have good weekends, and I'll see you next week. Our last week. Okay. Two-handed wave. Oh, raise the roof. Happy dance. Okay. All right. Bye, everybody.